And this is a work, as Marcello said, about diversity maximization. Diversity is a very beautiful and fundamental concept in nature. And despite what many narrow-minded politicians think, preserving diversity and actually maximizing diversity is very important, very beneficial, and so it's a great thing. Don't worry, I'm not going to go into social issues or political issues. I will talk about diversity as a computational problem, but as we will see in a minute, the problem has a lot of very concrete, real applications, and this is what stimulated actually this work. So this is an outline of the talk. I will give you the more formal, informal, and formal problem definition, mention some of the applications, give you some background on this topic, a brief summary of our results, and then I will give you a little bit more details about our results, the core set, which is the key technique to deal with very large data, so to extract a small representative of this data and then work on this small representative. And then this technique will enable us to develop efficient solutions for the new paradigms, MapReduce and streaming, that are used for dealing with large data sets. And then some further improvements about space of our construction. And then I will show you a number of experimental results on both synthetic and real data sets that show that what our techniques are effective and efficient. And then finally, I will conclude with some closing remarks and some pointers for future work. Future work, which is actually present work, because we are currently working on this, and we have actually very recent developments. If I have time, I will mention those. So problem definition and application. I try to use this. Okay. In broad terms, the diversity maximization can be defined as follows. We have a data set of elements. These elements are coming by, they are various, and there is some distance measured between pairs of elements defined. And what we want to do is to come up with a small subset of elements which are most diverse. So what most diverse mean, I will define in precise, in rigorous terms. So far, we think of maximizing the diversity between the elements of the subset, and the diversity is a function of the distance which is wired in the data set. What are the applications of diversity maximization problems? One application comes with the aggregator websites, for instance, Google News. There we have a set of elements, documents, for instance, and documents could be grouped into categories, clustered into categories. And we want to find, if you open the homepage of Google News, you will find a subset of news, of news entries, and this subset has to be suitably diversified. So it should be representative of the most important news that are there at the moment. And diversified, possibly if there are some categories spanning different categories. Another application comes from e-commerce. A consideration set. When you do online shopping and you search for a certain type of product, you do a query indicating some of the characteristics of your product. And then the website should return you a list of products that satisfy your desired characteristics. But among those that satisfy your needs, they should give you a sample of all most diverse products, so that you will with high probability find the one you are looking for. So again, you want to maximize the diversity of what is shown to you, complying with the requirements that you have indicated. Another application is facility location. If I have to set a number of franchise stores, I want to put them in space so that they don't compete with each other. So that I want to maximize the distance among the various stores. Or for instance, I have some facilities, strategic facilities that I want to place, and I want to place them in such a way that I minimize the probability of a simultaneous attack to all the facilities. Again, so they have to be distributed and their distances should be such that this property is guaranteed.
Can you say that this can be considered the dual of clustering problem?
This is a dual, very good point. This is a dual somewhat of the clustering problem, and actually our solutions exploit heavily clustering. So it's a theme of this work is the relationship between clustering and diversity maximization. Here comes a more mathematical formal definition. So we have given a set S of points in some metric space. It's, for us, it is crucial that the space is metric. So there is a distance function, D, that satisfies triangle inequality, and so it's a metric. Plus we are giving an integer k greater than 1. And then we are also given a diversity function that, given a subset of the metric space, returns some value that tells you the diversity of this set. There are different possible diversity functions, so I will define some in a moment. So if you are given also this diversity function, which must be a function of the distance in the metric space, then what I want is to find a subset of the set of points of size k that maximizes the value of this diversity function among all subsets of size k. And the k diversity of the whole set S is exactly the diversity of this small subset of size k. As I said, there are different possible definitions with different applications of a diversity of a set. So one is remote edge. The diversity of a set in this case is the minimum distance among the points in this subset. So if I want to maximize diversity, I want to maximize the minimum distance between the points. Another diversity function referred to as remote click. The diversity is the sum of the distances, or the average distance. In this case, I want to maximize the average distance. Or the other four definitions consider the points as a complete graph where each edge is weighted with the distance between 2 points. So in one case, remote star, we are looking for the star of minimum weight, and I want to maximize the star of minimum weight, or a bipartition of the points into 2 subsets of equal size, and I want to find a bipartition with the minimum weight of the edges among the 2 sets of the bipartition, and again I want to find a set S prime that maximizes this quantity, or a spanning tree of the points, or a cycle, a Hamiltonian cycle of the points. In all these cases, especially in the last 4 cases, I want to, in all problem except for the remote click, the diversity function is a minimization, and I want to maximize this function. Okay, all these problems are NP-hard. And there are, in the literature, there are a number of algorithms, approximation algorithms for these problems. And in this table, the best known approximation factor for sequential algorithms for these problems are reported. And they are all between 2 and 4. And also for some of the problems, there are lower bounds to the approximation factor. So basically they cannot be approximated with the approximation ratio better than what is indicated in this column unless P is equal NP. Except for the remote click case, this lower bound, it's a tricky thing because there is a reduction to a problem which is not known to be NP complete, but it's conjectured to be NP complete. Anyway, these are small details, but it seems that much better than this, at least for some problems, we cannot do. And then there are a number of specialized results for special cases like Euclidean spaces, so we have better approximations and still hardness results. And also recently, the remote click problem, where you want to maximize the average distance between the points, has been studied under the MapReduce constraint. So you add another constraint on the sets that qualify for the solutions using a MapReduce. Okay, our focus is on solving this problem, this diversity maximization problem, for very large data sets. As I mentioned at the beginning, when we are dealing with a very large data set, a key technique to solve problems, computationally intensive problems, is to extract from the data set a small subset, which is called the core set of points, that we can guarantee contains a good solution. In particular, in the case of diversity maximization, we want to extract a subset of the input such that the best solution that I can find in the subset is not too far from the best solution that I can find in the whole data set. And since we are talking about maximization, I want that the value of the best solution in the core set is at least a fraction beta from the 1 over beta from the best value I can find in the whole data set. Once I extract the core set, what I do, I compute the solution in the core set. If it is small, I can do some sort of exhaustive search, or I can apply sequential algorithms. The sequential algorithms I mentioned before are polynomial algorithms, but they are very slow. So they can have complexities that are quadratic or even cubic. So it is crucial to reduce the size of the input to apply those algorithms. So this is what I can do on the core set. And what the core set does eventually is to filter out some redundancy in the data set. So extract the points that were represented of the other points. In the context of distributed computing, when I want to solve problems for large input sizes and on distributed platforms, the concept of core set has been adapted, generalized. Suppose that your input is partitioned into a number of subsets, either because you want to use a distributed platform, so you want to split the input among different machines, or the input naturally comes split into different machines, for instance, different data centers, and you don't want to gather all the input in one machine, so you want to keep working in a distributed fashion. Then what we can do is that you can extract a core set from each set of the partition, and then merge together all the core sets and consider all these merged core sets as one core set, and then eventually compute the final solution on this merged, on the union of the core sets. And once you have a way of extracting core sets from different subsets that when merged together, they provide a good core set, then you have the basis for an efficient algorithm in MapReduce and in streaming. Very recently, in the last 2 or 3 years, a number of composable core sets for the diversity maximization problem have been developed. And in this table, I report the best known results. So for each of the diversity measures I mentioned, the first column reports the approximation factor that the core set introduces. The second column gives the best sequential approximation. So when you extract the core set and then solve on the core set, run on the core set the sequential approximation algorithm, you get as a final approximation the product of the two. So in the last column, you have the final approximation factor that is guaranteed by this technique. As you can see, these are constant approximation factors, but they are pretty high. And these hold for general metric spaces. And in these cases, the size of the core set is very small, so it's size k, so basically the size of the final solution. And these are composable, so you extract k subsets from each set of the partition, and then you have to put them together. Okay, stop me whenever you want to ask a question, even during the talk. To finish the background, let me briefly review what the MapReduce and streaming frameworks, which are now the state of the art, the standard de facto for processing large data sets. So in MapReduce, you have the data represented as multi-sets of key value pairs, and then you have algorithms that are specified as sequences of rounds, and in each round and the algorithms are executed on clusters of machines, and in one round you basically transform a set of key value pairs into another set of key value pairs by applying 2 functions. One, a map function, which is applied independently to each key value pair, and then a reduce function, which is applied to groups of key value pairs with the same key. And then from each round involves a shuffle of the data, because map and reduce function can be computed distributedly among the machines, but then you have to move the key value pairs and to assign send each key value pair to the machine that has to do the processing. And this involves a shuffle of the data. And if the data are very large, this is a very costly step. So when we develop algorithms in MapReduce, as a performance indicators, we use the number of rounds, basically the number of shuffles you have to do on the data, and the space required by the MapReduce function to operate locally on the data. And these are the two, and you have to develop suitable trade-offs between these two quantities. In streaming, instead, I have only one processor, and the processor has limited space to analyze the data. And the input comes as a continuous stream, and it is too large to fit into memory. So you basically have to consume the input as it comes without being able to store except for a very small fraction of it. And also you want to minimize the number of passes you do on the data. Hopefully you would like to do only one pass. If needed, you may do several passes if the data are stored in some tertiary storage or some place where you can retrieve them again. And here as a performance indicators, we use the number of passes. Again, we want to minimize them, and the space available to each processor, which is something that you also want to reduce. Now, if we take the composable core sets that are existing, that we saw in the previous slide, then it's fairly easy to, using these core sets, to come up with MapReduce and streaming algorithms. In MapReduce, basically you have the input split arbitrarily into subsets, and then compute in each subset a core set, and then put everything together and compute the final solution, and this can be done in 2 rounds in MapReduce. In streaming, you do one pass in each, in the pass, after you have seen a bunch of data, you compute a core set of the data, and you keep going like this. And it can be shown that using space, which is at most proportional to the square root of k times the size of the input, you can come up with a final solution with the approximation factor that we saw before. What did we do? What are our new results? First of all, we limit ourselves to a class of matrix spaces of so-called bounding doubling dimension. So in simple terms, this means that in my matrix space, given any ball of size R, I can cover this ball into a constant number of balls, 2 to the d, and d is the dimension of the space, 2 to the d balls of size R over 2, and d is a constant. For instance, Euclidean spaces of constant dimension under the L1 and L2 norm are matrix spaces of bounding doubling dimension. Also on a graph, shortest path distances, if the graph is not too expanding, can be proved to be of matrix spaces of constant bounding doubling dimension. And there are several other examples. So it's a relevant class of spaces. Under this limitation, we basically improved the core set constructions with a novel construction technique based on clustering that give an approximation of 1 plus epsilon. 1 plus epsilon is the approximation introduced by the core set, and then you have to multiply this by the approximation introduced by the final sequential algorithm. And indeed, using these core sets, we can come up with streaming and MapReduce algorithms, 1 pass in streaming, 2 round in MapReduce, that have an approximation ratio, which is the best sequential approximation ratio, plus epsilon, and epsilon is any constant that you provide. And the space required in the streaming and in MapReduce is given in this formula here. So for streaming, the space is order k divided epsilon to the d. So epsilon is the decides how good the approximation must be, and d is the dimension of the space. For MapReduce, we have square root of k times s divided by epsilon to the d. This is only for 2 of the diversity measures, remote edge and cycle. For the other diversity, we need a factor k more space for streaming, and factor square root of k more space for MapReduce. And in this case, where the space, there is a little blow up in space, we can reduce with some improvement the space requirements, but we need an extra pass or an extra round in streaming and MapReduce. Okay? Any questions so far? Okay, let me give you the main idea of our approach. So we are given an input data set, S, and let's call opt the optimal solution that we don't know, of course, of this input data set. So opt as size k. Our main idea is to compute a core set such that for each point in the optimal solution, there is a proxy in the core set which is close enough. The proxy in some cases has to be distinct for each point in the optimal solution, some other time is not distinct. With small distance, I forgot the word distance there. So how do we get a core set with this property? We partition the set S into a number of clusters k prime larger than k, which is the final size of the solution, so that in order to get a small radius for these clusters. And k prime is a function of the doubling dimension. Then we take as a corset just the cluster centers, and in some cases this will be enough. If the proxies of the points of the optimal solution have to be distinct, then together with the cluster centers, from each cluster we have to take a number of other points, at most k minus 1 point, so that altogether we take k points from each cluster that we call delegates. The term delegates came because we were doing this work during the American elections, so the delegate was
Going back to politics, right?
Going back to politics, yeah, I want to go back to politics. Okay, so this is the idea. Let me give you an example. Suppose that this is our initial point set, and we are looking for diversity maximization, so subsets of size k equal 3, and suppose that we fix k prime equal 8. So we do a k prime clustering, so we
partition is a random one?
This is not a partition, this is the input data set. Yeah. This is the whole data set.
But then you get the first partition?
And I get the first clustering. No, I want to do a clustering to minimize the radius, and I will talk about this in a...
Sorry, this is a single partition, meaning that you have to do this for every single partition of inputs.
Yes, I'm not talking about the composable corset. I'm just talking about, forget about the partition of the input. I have the input in one machine, and I want to cluster the input into clusters with small radius. K prime is the number of clusters. In this case, k prime is equal 8, and in red you see the center of the clusters. So as a first approximation, if I want to solve the diversity maximization problem, I can take the red points and then use them as a corset and then solve the problem on these red points. In some cases, this will be enough. Okay? If instead I want an additional property that for each point in the optimal solution I have a distinct proxy nearby, around each center I have to take a number of other points. So I take from each cluster the center and suppose 2 other points, if there are 2, or less if there are less points in the cluster. Okay? So altogether I end up with k prime times k points, k prime clusters, k point per clusters in this case. And this will be my corset. And then I will compute the final solution in on this corset. Some technical notions. So let me call Rk the minimum radius of any k clustering of the point set. The radius of a clustering when a center for each cluster is given is the minimum is the maximum distance between the center and any point in the cluster. So let's call it Rk, the optimal minimum radius of a k clustering. And let me call rho k instead the maximum minimum distance between k points in S. Given k points, I consider their minimum distance, and then if I maximize this over all subsets of k points, this is the farness rho k. Now it is easy to show that Rk and rho k are related in this way. So Rk is less than or equal than rho k. The proof is simple, but just me give you an example to show what I'm talking about. Suppose that this is a point set, and suppose that for k equal 5, these 5 points are those that maximize their farness. So the minimum distance between these red points, which is this distance, is maximized over all sets of 5 points. I hope this is the case. I mean, I constructed example, but it seems that more or less is the maximum minimum distance. Now, if I take these red points as cluster centers and I clusterize all the points around them, then you can see that with clusters of radius smaller than rho k, I can cover all the points. This is not a proof, but this gives you an intuition that Rk is, and this is this clustering, of course, is not the optimal one, but the optimal one will have a radius which is smaller than this. So Rk will be less than or equal than rho k. Why do we need this? We'll come to it in a moment, but we can easily show that if our point set comes from a space with doubling dimension d, given k, if I take k prime equal 16 divided by epsilon to the d, then when I do a clustering with radius, an optimal clustering with k prime clusters, the radius of the optimal clustering with k prime clusters is less than or equal than epsilon divided by 8, the radius of the optimal clustering for k clusters. So with spaces of bounded doubling dimensions, if I increase the number of clusters, I can control how the radius decreases. The radius decreases in a friendly way for our purposes. Okay, now let's put all the pieces together. Let's focus for simplicity on one of the diversity problems. So remote click, I want to find the k points that maximize their average distance. And suppose that, let's define rho as the value of the optimal solution divided k choose 2. So basically rho is the average distance among the optimal k points. And it's fairly easy to see that rho will be greater than or equal to rho k, so the maximum farness between k points, and greater than the minimum radius of a k clustering. So this relation holds. Okay, now comes the main theorem that says that if I take a corset, like I said before, taking a k prime clustering, taking the center of the clusters plus some delegates around these centers, and k prime has this relation with k, then the corset is a 1 plus epsilon corset for S. And the size of this corset is proportional to k squared times 1 over epsilon to the d. Which is independent of n.
D is
The dimension of the space. So this tells you that if the intuition is clear, if I partition the point into small clusters, and from each cluster I take a number of representatives, I know that for each point in the optimal solution, that point will be in some cluster, and it will have a representative which is close enough to that point. How close? Well, it will be close, as close as the radius of this clustering. And I have shown you before that the radius of this clustering is away from the radius of a k clustering, and then away from the average distance of the optimal solution. So how much time do we have left?
some 20 minutes.
Okay. Perhaps I don't go into the details of the proof, but with all this property, if you put the pieces together and using the triangle inequality, then you can show that once you're given the corset and consider the proxies of the optimal solution that you took from each cluster, then these proxies provide you a solution for the diversity maximization, which is not too distant from the solution provided by the optimal points. And the distance is a factor 1 plus epsilon. These are very trivial calculations using triangle inequality. Okay? So this is the general approach. Do a good clustering, take delegates and points from each cluster, and then this gives you the core set. And once you have the core set, you apply the sequential algorithm. But who gives us the good clustering? We know that computing a clustering that minimizes the radius is an NPR the problem. It's a famous K-center clustering. However, there are good approximation algorithms for K-center clustering. In particular, the very well-known farthest first strategy. You start from a node, from a point, you take the farthest point from it, and then the farthest from the first two, and the farthest from the first three, and so forth. You get a two approximation to the good clustering. A two approximation is good enough because we have already the epsilon, and we can play with the epsilon to absorb the two approximation. Okay, and now we have a strategy to compute one clustering. What about if we have our input already partitioned into subsets in different machines, in different data centers? We can try to do clustering in each subset. And if we do clustering in each subset, it is easy to see that you still get, when you combine all the core sets that you extract from each subset, you obtain a good core set in general. In this case, if your input is partitioned into L subsets originally, and you extract a core set using clustering from each subset, then you find a final merged core set will provide you a 1 plus epsilon approximation, and the size is L times k squared times this factor in epsilon and d. Okay, so now we have the tools. How do we apply these tools to get a good MapReduce and streaming solutions? Well, MapReduce is simple. So initially you have your input is partitioned among several machines. In each machine, basically with one reduce function for each machine, you compute the core sets from each set of the partition, and this will be the first round. In the second round, you aggregate all the composable core sets that you have computed in each machine into one machine, and then applying in one reduce function the sequential algorithm, you obtain the final output. And if you take into account the space that you require for the initial partition of the input, and then for the final aggregate core set, you can easily play with the sizes and come up with a strategy that uses space, which is k times n. N is the input size, square root of n divided square root of epsilon to the d. And again, the approximation guarantee is the best sequential approximation plus epsilon. You can slightly improve this by either assuming that the input is initially partitioned at random among the machines, or add an extra round to do a random shuffling of the input. If you do a random shuffling, then the k factor becomes a square root of k log n. And if k is larger than log n, this gives you an improvement in the space complexity. And if this is still too much space, you can apply this strategy recursively. By doing recursively, the approximation guarantees becomes worse, of course, but then you can eventually fit the strategy to any memory size that you want. In streaming, instead, we have an additional problem, because in MapReduce, in the first round, you have subsets in each machine, and in each machine you can apply the farthest first clustering strategy, sequential clustering strategy. In streaming, there isn't a streaming version of the farthest first clustering strategy. So we have to come up with a different clustering strategy. And there was a work by Charikar and other people done in 2004 that gives you a streaming algorithm for K center, K prime center, which has a worse approximation, 8-factor approximation. But again, as for the farthest first strategy, a factor 8 can be absorbed by the epsilon. So it doesn't change the whole picture. So we can do in one pass the calculation of the corset. Once you have the small corset in main memory, we do the sequential algorithm. And so we do it in one pass. The space required is k squared over epsilon to the d. Again, does not depend on the input size. And the approximation guaranteed is sequential approximation plus epsilon. Okay? This is for the remote click problem. For the other problems, you have similar results, except that for remote edge and remote cycle, they are slightly simpler, so the space goes down by factor k. Now, the space can be further reduced. In which way? Let me just tell you intuitively. Let's not go into the details. So our approach is to do a clustering and take from each cluster k delegates. So those k delegates are heavy because k times the number of clusters, then this gives you k squared, and then when you compose them, it's a factor k more. Can we get rid of these k delegates? We can indeed, because from each cluster, we just take one point and then represent the delegates as copies of the same point. Even if they are not exact points, but then it is sufficient. We just need to prove inactivity of the proxy function. So it is enough to work with copies of the same point. But if we have copies of the same point, we don't need to represent them explicitly. We can represent the copies as a multiplicity. So we basically represent a corset, a generalized corset, where each point indeed represents a number of copies of itself. And with such a corset, we can show that the sequential algorithm can be adapted to work with multiplicities. So to count each point as several replicas of itself. And then we can extract a final solution working with these virtual replicas. Once we have the virtual replicas of the final solution, then we can do a pass over the whole set of points and map each replica to a distinct real point, going back to the clusters. But the corset and the sequential algorithm for the final solution are applied to this generalized corset that uses this multiplicity, so that saves a factor k in the space complexity. This is the idea. The details are a bit tricky, but the main idea is the following. Okay. And this works also for the both streaming and the MapReduce. Let me finish with mentioning some experiments that we did. As a data sets, we used, as I said, both synthetic data and real data. Synthetic data were points generated in R3 from 4 million to 1.3 billion points. And as a real data set, we used the data set of music songs of about 250,000 music songs. Each song was, we used a bag of words model for representing the songs, the cosine distance. And as a platform, we ran our algorithms on a 16-node cluster with these characteristics and 10 gigabits per second internet. And for MapReduce, we used the Spark implementation. Spark is the most popular framework together with Hadoop for MapReduce-like computations. And for streaming, we did a simulation of the streaming environment. This is our cluster. Okay, the first experiment, we wanted to assess how the parameter k prime, so the number of clusters that we use to compute the core set, affects the quality of the solution. So in this case, in the x-axis, we have k, the size of the set of the final solution, and then the different bars are different values of k prime. K prime ranging from k to up to 1000, k prime equal 1000. And you see that as k prime increases on the y-axis, we have the approximation. The approximation here was measured again against not the optimal solution, because we couldn't compute the optimal solution, but we compute the best solution that we found in many iterations of the algorithm. So with respect to the ideal or to the approximate optimal solution, by increasing the value of k prime, you see that the approximation factor goes down. Although in this case, for small value of k's, already we have a good approximation factor, but then we go down almost to approximation 1. So the technique is effective, and here you see the trade-off, because larger k means larger space. So if you have more space and also more time to compute the core set and the solution, then you will get a better approximation. Then we compared our algorithm together with the state of the art. The state of the art was another algorithm using core sets developed in 2015. And here we used the full power of our clusters, so all 16 machines. And we had to use a small data set, because the other approach, the previous approach was computing the core set using local search, which is a very slow algorithm. So we couldn't go beyond 4 million points. For our algorithms, we used k prime equal 128, and for different values of k, these are the approximations. We did better, but not much better. But in terms of time, we did 3 orders of magnitude better. So this is in seconds. We are about 1 second, and their approach took between 800 and 4,000 seconds. And then we measured the scalability using the synthetic data. We wanted to see how the time increases with respect to the number of points, going from 100 million to 1.3 or 1.6 in this case billions. And you see that there is a sort of linear scalability, which is basically due to the initial step of computing the core set. And this is the scalability with respect to the number of machines. So in this graph, you see the number of processors in the x-axis. One processor is the streaming algorithm. We use the streaming algorithms because if you use the MapReduce for one processor, there is the overhead of MapReduce, so it wouldn't be fair as a comparison. And these are 100 million points, and you see that actually there is a super linear speed up when you increase the number of processors, at least up to 8 processors, because both the size of for the 2 rounds improve by a factor proportional to the number of processors. Okay, so the approach seems effective and efficient. Conclusions. So we came up with a new core set construction for composable, not composable, and composable core sets that introduce an approximation of 1 plus epsilon. And these are the first core set with such an approximation guaranteed, but only for doubling spaces, so spaces of constant doubling dimension. And the main primitive, the main tool, is the clustering K prime center, and this shows the relation between the two problems. And we can get space savings through the notion of generalized corsets, which is a novel notion that was not introduced to the best of our knowledge before. And then the experiments, both on real and synthetic data, show that the technique is effective, efficient, and scalable. And an important remark is that we are assuming that the space has a constant doubling dimension. But indeed, we are not using the doubling dimension as a parameter of the algorithm. We use the doubling dimension D only as for the analysis, for analysis purposes. And D guides the size K prime of the clustering that we used for the corset. But we know that the larger K prime, the better the corset will be. So even if you don't know the dimension of the space, if you do K prime as large as you can, based on the memory you are available, then you will do the best of this technique. So you can apply this technique without knowing the doubling dimension of the space, just maximize K prime within the limits you have of memory. Future work, well, there is still some space for trade-offs between the accuracy of the solutions, the number of rounds, and the space. As I said before, when you have very small space in MapReduce, you have to apply the algorithm recursively, and this increases the approximation factor. There you can work to decrease the approximation factor. We want to extend this approach to other broader classes of matrix spaces, or to incorporate other constraints. For instance, ensuring that the K most diverse points are not only most diverse among themselves, but they also represent regions of the space which are highly dense. So incorporate density somehow. Or a matroid constraint. So you want the K points of the final solution to satisfy some matroid constraint. We have recently showed that for certain type of matroid constraints, partition matroid constraints, then our approach can be adapted. There is an increase in the space complexity, but still provides you a 1 plus epsilon corset. And we are trying to extend it to more general matroid. And that's it. I'll stop here.
Thank you very much.
Sure.
The thing about density that you you already have in the notion of density in your algorithm when you compute.
Not exactly, because
Go back.
I know what you mean.
It's a kind of BD scan, let's say.
No, because I don't get. Okay. No, let me go back here.
Yeah, here.
Okay.
When you say I bring the.
Okay, here. When I compute the clustering, this clustering, my aim is to minimize the radius of the points. So in this case, the clusters are dense in this example. But suppose that, for instance, you have some outliers that are very distant, like the one up here. If that outlier is not close to any other point, you will take that as a cluster by itself. So in the technique I said, from each cluster take the center and k minus 1 delegates. But if you don't have any delegates, it's okay. You take as many as you can up to k minus 1.
Okay.
But if I have none, I take just the cluster center.
But I was in the next slide. Here. This slide here.
Okay?
In which you require to bring key points per cluster.
If there are key points, I could end up with a clustering where all the points are in one cluster and the other clusters have only the center.
Okay.
In that case, there will be only one cluster which is dense, and the other are not. That cluster is dense, but then as a final solution for diversity, you will get those points that are outliers, plus one point which belongs to a dense cluster.
So consider, for instance, Amazon selling fridges. All fridges are more or less the same, and there are some outrageous fridges, one with diamonds and so on. You will get all those crazy ones and just one representative for the fridges that everyone wants.
And I don't want to present the user with weird fridges. Perhaps a few of them, but I want to present a more regular one. So that doesn't give you any guarantee. So if you only want to maximize diversity, you may end up taking, even the optimal solution could consist of outliers. But if you impose that in your final solution, you want diversity, but also you want representativity, then you have to incorporate something.
I was wondering whether in machine learning, one important problem is feature selection, right? Feature selection, I think, can be pretty well formalized using this notion of maximization of the diversity, given n features with big N.
I want to find the K.
Exactly. So I was wondering, in terms of application, if these ideas have ever been applied to feature selection in machine learning.
Diversity maximization, not that I know. I mean, the applications are mostly in the realm either as a pre-processing step for some learning algorithms, like farthest first or something like this, or e-commerce, facility location.
Historically, it's been developed in operations research in facility research.
So there could be an interesting avenue of, to explore.
The problem of feature selection can be formulated this way. You have a notion of distance or whatever between features, and given a large number of features, you want to extract kind of a small subset of as diverse as possible. So
can you define a distance between? Yeah.
Okay.
Yeah, that would be very good.
One more thing I wanted to ask you. So K prime here is kept fixed, right? It's a parameter.
Yeah, you decide. It's a tunable parameter of the algorithm.
Would it make sense to have a K prime which depends on the local structure around the centers? So in this case, you have a variable number of K, but depends on the structure.
Yes, as long as you guarantee that the radius of the clusters, the radius of these clusters, if you can guarantee that this is small with respect to the average distance of the final solution.
Yeah.
As long as you guarantee this, then you can...
Let's say if you want the hard guarantee, of course you have to do that.
Okay.
Heuristically, perhaps.
Oh yeah, no, if you want to...
Or what do you want?
More questions? Yeah, I was wondering when you said exploring algorithm space. In machine learning, one of the usual things is just like using a kernel function that embedded your magic space in a higher dimensional magic space in order to better separate the point. In our setting, you can better separate similar points, even if apparently you increase the dimension of the space.
But if you separate the similar points, aren't you obfuscating the final solution?
I think that this method is just to better separate the point in order to find better the similar point. So the clustering is more easy. I think.
Okay.
I don't know.
Yeah, the point, I mean, in machine learning, you have a bunch of feature vectors, and in some high-dimensional space, and you want to separate them into two classes.
Yeah, like a support vector machine. Yeah, you can one of the kernel. Yeah.
Exactly that. So you project these points in a higher dimensional feature space, where you can separate them very easily, say with a linear.
So you think that this will improve the cluster, make the clustering easy?
Yeah.
Yeah.
Locally
In
in a single core in the MapReduce.
Yeah. In each machine you do this. Yeah, that could be a possibility that we haven't explored.
One problem here, I guess, is that SVM are very unscalable. So if you have lots of data, it is very difficult to do that.
Well, if your data is very large, in each machine you still have a large data set. And that's actually our approach compared to the previous ones that are using local search. Even when you are distributed among several machines, but still in one machine, when you have 1 billion data, with 16 machines, you will get about 100 million points. Then doing local search on 100 million points takes hours. So we have to do something very fast in each machine. So if the kernel idea could...
Maybe another issue is that if you use kernel on each of a separate core, no, but when you combine them in the reducing phase, you have to have the same dimensional space, otherwise, how you can do it?
So otherwise we need to somehow homogenize.
Yes, exactly, get back to another common space.
This is a problem because
But you can
if you
perhaps
read days or something, you go into the data space for all.
We haven't, this is a very new work, so there are several questions. Yes?
A question that is, I'm a statistician, so it's a little out of field. I'm going
Not
on,
quite.
on the question that Marcello was taking out. That is, in statistics we have the problem of reducing the dimensionality of the problem. Quite often we have an incredible high number of variables affecting, besides the number of people that are characterized like that. So one of the problems that we face almost every day is how to reduce the dimension. So in your approach, if I understood, in your approach, there could be the possibility to find one subset with the maximum diversity, and the maximum and the distance that you use to find the maximum diversity can be the relation that there is between each of these, let's say, feature variables with one variable that you want to study, analyze, model, optimize. So when you address the problem of modeling this data, the problem is to find the best variable that affects the Y. So when you say the best, you go to find the set of variables that are not related. You know, one very old procedure is the principal component analysis. I don't know if you know. But it is the opposite of this. In the principal component, you go to find the ones that are very similar. This is the opposite, and it's very interesting. Thank you for this report, because it's very interesting. And the idea is that what I want to ask you is, do you see the possibility to build up one subset that is the best? And this one subset is the subset that is composed of all the points that maximize the distance, because this will be the best.
What is your notion of distance in this case? Distance from one...
It would be the dependence between one of these variables with the problem that you want to, the variable that you want to analyze. For instance, let's say my group and me, we are working in molecular biology. We are trying to build a composition to find the best molecule that is the best activity. The activity is related to thousands of variables. These thousands of variables are labels. That is another problem. Let's keep apart. Suppose they are not, but then we can figure out what to do. So the idea is that among these 1,000, you like to find the best. What does it mean, the best? The one that can affect more the activity of the model.
But let me understand one thing. Suppose that you do a scan of all of them. For each of them, can you measure its quality, how good it is. So can you do a sorting of all the, based on their...
yeah, you can do a sorting, you can do a set, or you can find possibilities.
Because if you do a sorting, then I would say one could do a sorting and then take the top k ones. But then, so it's a slightly different problem. If you can, for each variable, assess individually its quality, then one thing, sorting in that case would be the primitive to use. If you instead have a distance between pairs of variables, then you have to resort to this kind of thing, because you want k variables that are mutually distant from one another. If I understand correctly, you are talking about a set of variables, each of them very distant from some reference.
They are both the problem, of course.
Okay.
They are both the problem, because some are behaving in a very similar way, so the idea is that, you know, to consider like in principal component analysis, we take away the one that don't affect the result. But there is also the other one.
I think that in general, as long as you can define a distance between two elements, and this distance satisfies the triangle inequality. Actually, for our approach, you need a triangle inequality, but there are in the literature very recent works that work for very general distances, even without triangle inequality. So, but you need a sort of, you need to define your diversity based on a distance, on some notion of distance. In that case, this framework, this diversity maximization framework applies. If instead you have to consider each element individually, then I would go for a different approach, like sorting, ranking, things like this.
Okay, just a very quick comment. I mean, this idea, going back to the relationship between this idea and clustering, maybe we can discuss this later, but it reminds me of our dominant set framework, which I explained to you when I listened to you, which is exactly the opposite. The dominant set is a single cluster where the distance, the similarity within the cluster is maximized.
Okay.
So I was wondering, and maybe we can discuss this later, whether we can use this framework for finding dominant sets and last sets. It's just the dual in some respect. Because ours is not really a clustering framework where you want to partition the input data. Ours is an approach where, given a bunch of data, you want to extract a single cluster with properties
that maximizes.
So if you take the dual of this problem, I think this is exactly the problem I mentioned, I suspect. And then I was wondering whether this very framework can be applied to find dominant sets.
So we want to come up with a k-diverse subset, and perhaps clustering around those k-diverse points, you find one clustering which is related to the clustering that maximizes.
Well, if you do a n minus k diversity, so you take out the n minus k most diverse points, you are left with the k similar, but the complexity will be atrocious.
And I mean the other way around. No, I'm talking about, you talk about distances, while in our framework you use similarities, which is dual. It's exactly the opposite. So we try to maximize similarity.
Okay, so you have a notion of similarity between two points.
Exactly. And if you have distances, you can take, say, some Gaussian kernel, you transform a distance into similarity. So I was wondering, just swapping the two notions of distance.
Yeah, okay, no, I did it.
I take your approach, which is kind of...
Okay.
I remember, I don't know why I have this feeling that I felt the literature on this kind of problem is pretty large, because in facility location it was called p-dispersion and so on. And now, very lately, you must have read something where they were somehow mentioning cars of dimensionality and applications of dispersion to dimension.
Yeah, I don't have a memory of it, but it could be. And Why not? I mean, one had to take a piece of paper and pencil and do the calculation, but this dual perspective could work. Yeah.
Because this notion of core set, we have it also in the dominant set.
Yeah.
Because it's the prototype for each dominant.
Exactly. Okay, we can discuss it later. More questions? Okay, so if not, thank you again, Andrea.
Thank you.
Sì, le slide,